Hello to all. This is a short video discussion on something we call data transformations. So here's the deal. Sometimes your data doesn't behave, and for a various number of reasons, it's not performing the way it needs to in order for you to do multivariate analysis. So it is either out of scale, there are problems with your data, or maybe there are assumptions that are violated. So violated assumptions might be lack of normality, lack of linearity, lack of homoscedasticity. So those are things that you want to be aware of and think about. And if we can adjust our data and try to correct for these failed assumptions, then that's what we want to try to do. So that's our whole idea of a transformation. Now, we may make some adjustments in advance. And so here's the deal. Sometimes our data is not scaled the same way. Sometimes we don't have distributions that act the way they're supposed to do, or maybe the assumptions are not made properly. So data transformations then provide a means to modify variables to help correct for violations of statistical assumptions. And what might also happen is relationships may be better or more clearly explained once the data has been transformed or adjusted. So adjustments, first of all, are when you make some type of a data change or modification because of maybe some way the data was collected or something along those effects. So like for instance, say you have a variable like income, and income is measured in thousands and thousands of dollars. So you may have thousands in terms of the magnitude of the variable, but you may be comparing that to maybe the number of monthly purchases, which is maybe 1 or 2 or 10 or something like that. So we have a different scale going on here. We have two variables scaled on a differently, and when you try to compare a number in the hundreds of thousands to a number in the ones, sometimes you lose the effectiveness of that. So if you have, or here's another example, what if you have a Likert-like scale that's scaled on a 10-point scale, and then you are using also Likert-like scales that are on a 5-point scale? Then you're dealing with different scales, and you might not be able to interpret the results as cleanly or as easily. So sometimes we want to do something called either standardization or normalization. So when we statistically standardize our data, we make it so that the data is all, like when we take our data, we take the mean of our data. If it's been standardized, then we have a mean of 0 and we have a standard deviation of 1. Okay, so there's a simple standardization formula that can be used. And so again, this helps take out the effect of non-scaled or differently scaled data. Okay, so this is actually a common thing to do. Sometimes people refer to it as normalization, but it's really not. It's really called standardization. When we standardize the data to, and this would standardize it to a z-score, something like that. Is what we would want, and we'd have our new standardized score if we perform this on our variables. So data standardization. The other thing that we do is we apply some type of mathematical approach to transform the data. And so you can do any number of different corrections, if you will. So you can take an inverse, for instance, of your data, 1 divided by your response, or take the square root of it, or take the log. So take the natural log of your data. You can square your data, you can cube your data, you can do any number of different techniques here that would help adjust for maybe the kurtosis issues that you might have. So if your data is suffering from different issues of peakedness or flatness for kurtosis, or if your data is skewed, then you can try several of these different approaches to try to correct your data. Okay, you can also, if you note that your data is dealing with heteroskedasticity, applying only to the dependent variable, you can again do some of these different techniques. So we have square roots, we have inverses, right? We have arcsines that can be dealt with or used as well. Okay, so these are all different approaches where you take your response and you create a brand new variable, which is the transformed variable, and then see if that will help. So we test for normality or test for heteroskedasticity or linearity, and then we perform the transformation, and then we test for those things again to see if any improvement has been made in the actual variable. And sometimes there's only very, very, very small improvement. Sometimes the data is not improved at all as a result of these types of transformations. It takes a lot of trial and error and just kind of a gauge or a researcher's keen insight to determine whether it was worth doing the transformation or not. Okay, so linearity again, so when we have linear or nonlinear data, when we're looking at our data set, we want to make sure that the relationship is like linear, like a straight line. You'll notice on all of these examples here, we have a curved line. It's either concave or convex. So this one here is concave. This is convex, negatively skewed, and so on and so forth. And we have some potential methods in which we can try to correct for this. In this case, we have a y on the vertical axis and an x on the horizontal axis, and we can make different log changes. So taking the natural log of these variables while also taking inverses of the other variable simultaneously, then this might be something that we do to correct the relationship of linearity. Okay, so again, all of these are just different things we can do to data, and we're creating new variables, and then we're looking at the result to see if indeed what we created new is better than what we had before as they relate to the assumptions that we had set forth. So is it more normally distributed after the transformation than it was before? Is it more homoskedastic or more linear than it was before? And that's the judgment call that we need to be able to make. Okay, so if we have multiple variables that are heteroskedastic or nonlinear, then we want to be able to calculate. We want to be able to test for this and see if these improvements have been improved. Again, we can look at some different standards here where we look at either the standardized variables, and if those standardized variables, kind of like we would look at for outliers, if they're way outside of the norm, then we might be able to make some correct. One thing to remember that's actually important when we're dealing with heteroskedastic data, so again, where the variance between two variables are expanding, you want to make transformations to the dependent variable in that case. So that's, we want to be able to do that. If we have other issues of nonlinearity, then we may also include the independent variables, but that's heteroscedastic data variables or relationships need to be adjusted by the dependent variable and not the independent variable in that particular case. Okay, so the final point or last point to make here would transformations may change the interpretation of variables. So in other words, be cautious about how you use these. As we change as we change a variable, we're creating a new variable, and so we want to make sure that we take into account possible new interpretations of what that variable means, if we can. So transformations, again, they can help you out, or you can work on a particular variable or set of variables, and transformations may not have a huge impact either. Key thing here I would suggest is if you have a sufficient sample size, then the sample is going to take care of a lot of problems in and of itself. The other thing is we have a lot of robust different multivariate techniques that may, for instance, take into account some of this issue. So, like for instance, if you have a discrete variable like purchase, like either somebody purchases or they don't. It's a binary outcome. They either purchase or they don't. Well, that variable, they either purchased or they didn't, that's not normally distributed. So it's not a normally distributed variable. So, and there's nothing you can do to make it normally distributed because it's binary. So we can't do regression then as a result. It cannot be the dependent variable in a regression. However, what we can do is we can do something called logistical regression, or a logit model or a probit model. And logistical regression accounts for non-normally distributed dependent variables. So even though your data transformation may not work, or maybe you violate some of these assumptions, keep in mind that the multivariate approach or technique that we use may possibly account for some non-assumptions being met. Okay, so use caution when you're doing transformations, and try a lot of different types of transformations if you want. Compare before and after effects of the transformation to see if your data improves or not.